If some, I don't know, from US, if they will join, and they can join anyway.
Yes, we can wait for a couple of more minutes.
Sure, Daksh.
I just have a query. I just want to ask that the last session where I covered the RNN, I was not able to cover it fully, but the last session where I covered RNN, was it a bit like too fast going, or it was okay? Eh,
The last session was a variational encoder, I think, Daksh.
No, the coding session.
Okay, okay, coding session. Okay, okay.
Yeah. Actually, because that was the first time I actually covered the RNN part.
Daksh, the next time, can we take some the real data set, like not from the MNIST, because it is already like inbuilt data type and the APIs are available to access those data. So it's better, can we generate the data and pre-process the data, because I think end-to-end practical is also would be more beneficial for us.
Yeah, actually, yeah.
Because I heard like pre-processing also much more important, like in case of graphics data, those things. Because most of the time we
Yeah,
did
that can be done. I mean, but
yes.
yeah, I understand the point. But the problem is in collab, it's a bit restricted on how much data one can use.
Okay.
Uh,
Actually, I'm very much not aware of this collab. This is very new to this platform actually.
yeah.
Yes, yeah.
Hmm. I can actually do one thing. I can.
I think that we had discussed something. You'll be taking some practical example. I think it was discussed. Uh,
Yeah.
so it's better
Actually, the
something.
issue is I tried to get it through collab, but the data was really big and it was not coming in collab.
Okay.
So basically, what I did was I got my image data, and the point was that I will show how to load the image data if it's in the hard disk, and that was what I wanted to do. But the problem was the data was not coming into collab,
Okay.
so that's what was the problem. What I can do is next time what I can do is I can actually work on some real-time data, but it won't be via collab. So I will make a Jupyter notebook here
Okay.
so that I can communicate via my server, and I
Yeah.
will show how it's running on real data and everything on my server, and I will share the data and the codes with you. So it won't be on collab, but so something like that might work.
Yes. Yes. Yeah. And the problem comes in this machine learning part, like generating a data set also. And in case of MNIST, we already have everything available. So sometime end-to-end learning is not being done.
Yeah, generating a data. Yeah.
Yeah. Just
So
take
by
some
generating a data,
data set kind of.
you have means you have images. So by generating a data, what
Right.
I can show is that, let's say for a simple classification task, I have a folder of the data,
Okay.
and inside the folder, let's say I have
Oh,
multiple folders for multiple classes, and
yes,
inside
yes,
each
yes,
folder, then there are images. So I can
yes,
show
yes.
that how one can
Okay.
read these images with the labels and everything.
Yes. Just a small example. How can we proceed further, and from where we can get the data also.
Okay. It would be better that if I share one of my data sets.
Okay.
So what I will do is, because again that if we work on any real-time data is a bit big in size. So I can find a way to share it, but the problem is it won't be able to run on Collab. So what I can do is I can actually show the running on my own system via my server here, and then share the data and code so that you guys can run in your own systems or something like that can be done.
Thank you, Yaksh.
Yeah, so for the next session, the first thing would be we will see about the, I will make a small CNN, just a classification CNN that will be reading the data from the hard disk. And again, I will create the data like the data is not structured, like all the images sizes will be different so that many things I can show that multiple things how they are handled.
Okay. And if you take the example of RNN again, then also it will be more good
Okay,
for us.
about
Yeah.
Yeah,
RNN.
Instead of CNN, RN. Yeah.
yeah. I'm also want that one.
Yes.
Okay, actually RNN, so I will have to actually see what kind of data I can use in RNN.
I think stock example is very popular one. You can take this data also. Stock.
Right.
Yeah, so I will take one of the,
Yeah.
and through RNN, what I can show is the reading through CSV files. That
Okay.
if you
No.
have raw
Yes.
data in the form of CSV files,
Yes. No problem. Yes.
so how can you read the data and format? Yes, yeah, I can do that. I can make a RNN problem with raw data from CSV files, some forecasting data, and we can work on that. Yes, sure. Okay.
Yeah, sure.
Thank you, Yaksh.
Okay, so shall we start or?
Yes, I think I can start.
Okay, so oh wait, I need to share my screen. Okay, so is my screen visible?
Yes.
Yes.
Okay. So basically, we'll be covering two things today. One is autoencoder and one is variational autoencoder. So autoencoder is pretty much basic. The reason I'm starting with autoencoder is so that I can actually start with a new API of making models of Keras. That's a functional API. Because I cannot make VAE with the sequential API that we have been seeing till now. So first we will be seeing the functional API, and to understand functional API fully, we will start with a simple system that's an autoencoder. So autoencoder is pretty much similar to how we did a CNN model. So it contains two parts, an encoder and a decoder. So the encoder will take my input image, and the encoder will downsample that image to a latent space representation, to a feature, to a latent feature, and then decoder using this latent feature will try to reconstruct that same image. Now, reconstruction of the same image does not make sense. So the task that we'll be using is we'll be using the denoising task. So our task would be that, let's say my input image is the noised version of an image. So how can I use an autoencoder to denoise that image? So let's say I have an input image which has a noise in it, and the encoder will take the noisy image, and the decoder will output the actual original image, not the denoised image. So how that can be done via autoencoder? So that is something I will be covering. And okay, so this is the simple picture of an autoencoder. There's an input image, there's an encoder model which converts into latent space, then there's a decoder model, and there's an output image. Okay. I have one question. Is my mouse visible in the shared screen?
Yes.
Yes.
Okay. Yeah, because so now so when we made a CNN contained convolutional filters and max pooling filters. So we already know what a convolutional max pooling filters are. So the convolutional max pooling filters will actually decrease the size of the input image. But after the latent space, I also need to increase the size of the feature so that I can get my input image back. I can reconstruct my input image. So for that, just how the max pooling works, I have another layer in Keras, that's upsampling. So upsampling is the complementary layer of max pooling. Like max pooling is a pooling layer, it decreases the size. Upsampling is a sampling layer which increases the size of my feature map. So in the encoder, I will be using convolutions for learning and max pooling for decreasing the size. Whereas in decoder, I will be using convolutions for learning and upsampling for increasing the size. Okay, so this is a new layer that we will be importing in this case. That's my upsampling layer. So upsampling 2D. So upsampling 2D layer will actually take a 2D, a 3D feature map in the form of rows, columns, and channels, and it will upsample it to some new rows, columns, and channels. So, and the upsampling will be on the 2D space, that is on the rows and column space. It won't change my channels. Like max pooling doesn't change my channels. Similarly, upsampling will never change my channels. So that's why it's a 2D operation, and that's why it's upsampling 2D. Okay. So whenever we are working with functional API, there's a layer that we have to use. That's an input layer. So that's a new layer that we'll be seeing today. That's an input layer, and I will show how and when we have to use the input layer. Now you remember from the previous ones. So from Keras, we have to import the API that we will be using. So from Keras.models, we imported the sequential API in previous cases, but this time we are importing the model API or the functional API. So if I want to use the functional API, the thing that I want to import from the Keras.models is model function. This model function will actually provide me a deep learning based model using model API, functional API. So rather than sequential in previous cases, we have model here. And finally, we'll be working on MNIST dataset. So that's something that we'll be using. Okay. So as previously, we are loading the dataset of MNIST. Okay. So MNIST dataset contains Xtrain and Ytrain and Xtest and Ytest. So Xtrain contains all the MNIST dataset images, and Ytrain contains the corresponding labels. Xtest contains all the testing images, and Ytest contains all the testing labels. So here one thing is autoencoders are unsupervised in nature. So in this whole code, we won't be using Ytrain and Ytest at all. So whenever we are working with autoencoders, we don't care about the labels of the class. We are just trying to understand the images, some feature of an image, or doing some transformation over an image. So in that case, it doesn't matter from which class that image belongs to. So in autoencoder, the labels Ytrain and Ytest are redundant for us. We won't be using them. Okay, so in rest of the code, you won't see Ytrain and Ytest at all. But Xtrain and Xtest we'll be using because Xtrain contains my training images and Xtest contains my testing images. Now in Xtrain contains my images in the form of a 28 cross 28 array. So each image in my Xtrain is a 28 cross 28 array. Okay, and each value in that array is a integer value going from 0 to 255. So the very first task is to convert these values into floating point values. So the integer values. So for that, the function that we'll be using is the asType function. So it's a NumPy function asType which converts any given array into the type that we have provided in the brackets. So here we are providing float 32, that is 32-bit floating point an integer type array converted into a floating point array. And similarly, we will convert X test into a floating point array. Now, the original images, they are in the range of 0 to 255. So that's the range of images from 0 to 255. And we have to normalize the data. And normalization is always that needs to be done. So we are normalizing the data by dividing every image by the maximum value possible, that is 255. So here I am saying that xtrain is equal to xtrain divided by 255 and xtest is equal to xtest divided by 255. So by doing this, the range of the input and output has now become in the range of 0 to 1 rather than 0 to 255. And that's why you can see why it was important to convert it into a floating point, because if it didn't convert into floating point, this kind of division wouldn't have been possible, because this division needs to happen over the floating point rather than integer. Okay. Now, as I previously said that xtrain, the shape of xtrain is actually 28, 28. So xtrain, so each element of an xtrain is actually a two-dimensional array, that is 28, 28. And xtrain has 60,000 such images. So the overall dimension of the xtrain array is, so the overall shape, sorry, so the overall shape of the xtrain array is 60,000, 28, 28. Okay, so this is the shape of the xtrain array, and in which each of the image is of the shape 28, 28. But as we previously discussed, the network actually wants each image in a three-dimensional array. So any image that we are inputting into the network, it has to be three-dimensional. So even if the image is single-channeled image, we have to add the third dimension as one. So we have to convert this array in the form of 60,000, 28, 28, 1. So we are just adding another dimension, but that dimension is not giving us any information. But given any input image, we have to convert that image into a three-dimensional array. So that has to be done if we want to input in keras. So for doing that, so you can see the initial size of the array was 60,000, 28, 28. Okay, and I need to convert it 60,000, 28, 28, 1. So the initial array had three dimensions, and I want to add a fourth dimension. So for that, what I can do is I can use the numpy function np.newAxis. So what this function does is, so let's say xtrain was my initial array, and that array had three dimensions. So I specified the three dimensions with colons. So first dimension is specified by colon, second dimension is specified by colon, third dimension is specified by colon. Okay. Now I want to add another fourth dimension into that. Now this fourth dimension was not present in the initial xtrain. So to add the fourth dimension, I will use the function np.newAxis. So wherever I want to add another dimension to that array, especially the fourth dimension to that array, I can use the function np.newAxis. So initially xtrain was a three-dimensional array which is being represented by these three colons separated by comma, and I want to add the fourth dimension in that array. That's been added by the function np.newAxis. So this thing is also similar to, I can also write xtrain is equal to np.expand temps xtrain comma 0, 1, 2, 3. So these two lines are similar to each other. So these two lines will do the very same task. So I can write this same line as xtrain is equal to np.expand dimensions xtrain 3. So here what I am saying is I want to expand dimensions of this xtrain array at the third axis. So that is 0, 1, 2, third axis. So that is where I want to expand the dimensions. So either I can write it in this way, or I can write it in this way, that is at the third axis. So this was a zeroth axis, that's a colon, first and second. At the third axis, I can give the function np.newAxis, it will create the third axis. So these both the commands are synonymous to each other. You can use any of the commands. But previously we covered expand dimensions, but in this code I wanted to show the np.newAxis as well. So in this code I have used np.newAxis. So similarly, we did it for xtest as well. So we converted xtest also, we added a new axis so that now each image in my testing data also becomes array of 28 comma 28 comma 1. So I've added the channels information as well, that there it's a single channel image. So now my images are in the proper format that can be inputted in the network, and they are in proper variable type as well, that is my floating point, and they are in proper range as well, that is they are normalized, that is between 0 and 1. Okay. So I can create a validation data as well. So for creating a validation data, because testing data, we assume that we never have testing data till the very end time. We own, if we want to validate the network the way while we are training, we have to create a validation data. So as done in previous codes, the validation data has been created by the sklearn function train test split, which given any set of arrays will split these arrays into two sub arrays, and so we can get those two sub arrays so that we can so from the X train data we can get X train and Y train, where the test size is 0.2. That is 20% of the original X train data will go to Y train and 80% of the original X train data will go to X train. So now I have X train and Y train, in which sorry, X train and X well. Sorry. X train and X well, not Y train, X well. So basically, if I split X train, so 20% of the X train data will go to X well, and 80% of X train data will go to X train. So now I have split the X train into two arrays, X train and X well. So now I will be using X well for validating my and X test will be used for testing my network. Okay. Now, as I said, the task that we want to perform is actually we want to denoise. Okay, but the original data, the data that we have here, it's this data does not contain any noise. So what we will do is we will create an artificial noise and add the noise over our own data. Okay, so we will take the X train data and we will add the noise over the X train data to create the noisy input. So these X train data were original images, but now we are going to add some random noise in. Okay, so to add the random noise, what I'm doing is I'm taking the X train, okay, the training images, okay, then I'm adding a noise. So I'm adding a Gaussian noise in this case, okay, a normal noise, a Gaussian noise, okay. So I can actually create a random Gaussian noise. Okay, so to create any random Gaussian noise or random normal noise, the function that we use is np.random.normal. Now this function will give me random numbers in the normal distribution. Now every normal distribution have two parameters, their mean and their variance. So we specify the mean as location. The location is the mean of that array, and the variance I specify it as the scale. That is at what variance my normal distribution will create my data. And finally, the shape of the final output. So basically, how many data points it has to create randomly. So I can define that by shape, the size basically. So size, in size, I will give that how many data points randomly it has to create, and what is the shape of the final array that it has to create. Now, since this noise is being added over my explain data, so this noise has to be of the same shape as my explain data. So then only I will be able to add the noise over my explain data. So I'm saying that the size of this noise has to be same as the shape of explain. So whatever the shape of my explain data was, I need to create a random noise in the shape of explain. So what it will do is this function will give me uh, 4-dimensional matrix of the size same as explain, in which every value of that matrix will have been generated by a randomly used by a normal function with this mean and this variance. Okay, now the noise can actually noise. You can, because see, we had already normalized the data into 0 to 1. So let's say if I add a noise of 1, the data is already in 0 to 1, I'm technically flipping the pixel. And usually the noise is actually the noise factor of noise is is not the same as the range of my original data. So we are decreasing the noise by using a noise factor that is a 0.2. So whatever noise it's being generated here, whatever randomness it's being generated here, we are multiplying it by 0.2 so that we can scale down the randomness of it, and then we are adding on X train. So we are taking the input data X train, we are adding a noise, multiplying it by noise factor, and then we are getting my noisy X train data. So X train noisy is my noisy X train data that I am having. Similarly, I am doing the same for XVAL data, the same very noise on XVAL data, and I'm creating another array X valid noisy, and I'm adding the same noise over my testing data, and I'm creating another array X test noisy. So now I have three arrays: X10, XVAL, and X test, and three more arrays, their noisy versions: X10 noisy, X valid noisy, and X test noisy. Okay. Now, one problem while adding the noise can be that the range of X10 was from 0 to 1. Okay. But after adding the noise, there can be a case that my that some values have become negative and some values have become more than 1. But we know whenever, even if we get a noisy image, image in the real case scenario, that image will be in the range of 0 to 55, or it will be in the range of 0 to 1. So to remove those outliers or the values that are less than 0 and more than 1, we use the function np.clip. So what np.clip does is it will take an input array. So np.clip function, so this is the function, it takes an input array and it clips all of the values in that array by the range that I have provided. So I have said that clip all of the values in the range from 0 to 1. So it will take the whole number array X10 noisy, and then whatever values are less than 0, it will make them 0, and whatever values are greater than 1, it will make them 1, and whatever values are between 0 and 1, it will keep them as it is. So 0.5 will remain 0.5, but minus 0.1 will become 0 and 1.1 will become 1. So by using np.clip, I have actually made my noisy data also in the range of 0 to 1. That will be the case in testing data. So I have done this same for all the three noisy datas, that is X10 noisy, X valid noisy, and X test noisy. So in this, I have now my noisy data. So here I can show you some of the images of the noisy data. Okay. But it has added a lot of noise in this case. Wait.
So that this step will not be required in case of real type example.
Yeah, in real example, you will already have the noisy images.
Yes.
So in real example, you will already have the noisy images. So this line of code won't be required. But
So,
here I just.
So there also I need to clip or without clip.
No, so because whenever you have an image, by default, whenever you read any image, whether it be noisy or non-noisy, it will be in the range of 0 to 255.
Okay.
Okay, so there you don't need to clip. Here, the reason we are clipping is because we are adding some random noise. We want to preserve the property of an image that an image is between 0 to 255 only.
Okay.
So that's why we are clipping in this case. But in real time, you don't have to clip. So you can see here, you can see the noise that has been added in the MNIST data. So in the tree, there are some black, some grayness coming in tree and some grayness coming in the background as well. So you can see the noise that has been added. So now this is my input. That's my noisy images, and I need to create my denoised images via this. So for that, now I will be creating a model. Okay. So in collab also, the collab is not that well in running, so we will only run this model for 2 epochs. We won't run it for more than 2 epochs. Okay. And where I'm using in channels. Yeah. So in channel is basically a variable that I'm providing to tell what is the shape of my what is the number of channels in the input image. Okay, so that is my in channels. So in this case, the image is a grayscale image, black and white image. The number of channels of black and white images are 1, so my in channel is 1. But in the case of real data, the usually images are RGB. So in that case, my in channel would be 3. But in this case, I'm using in channel as 1 only. Okay. And here I'm defining the batch size, that I will be using for the for running my code. Okay. And here I'm giving the size of each of the image. Okay. So size of each of the image is 28,28. That is, my X size of the image is 28 and my Y size of the image is also 28. So here I'm giving the size of each image, and here I have specified the number of channels in each image. So if I say my input image, the shape of my input image is X comma Y comma in channels, that is 28 comma 28 comma 1. So that's the shape of my input image. Now, since we are using here a functional API, so we won't be using .add function. Okay. So when we are not using .add function and when we are using functional API, we have to create a input tensor. So a tensor that will be an input to my network. I have to create a tensor. So that is a gateway to the network where I will be putting my input images. So to create that tensor, I will be using the layer input layer. So this is the input layer here. So whenever I'm using functional API, I need to create my input where I will put the input. Okay. So to specify where I will put the input, I use the input layer. So my very first thing is I use the input layer. So what this input layer will do is it will actually create an tensor, knowing that on this tensor, the input from outside will come. That is, the images that we input to the network, they will actually go to this tensor. The name of the tensor is input image. So it will create a tensor in the name of input image where it knows that it will get some data from outside. Okay. And in that input tensor, there's only, we have to specify the shape of the tensor, that is the shape of the data that needs to come. So whenever we are using functional API, okay, so we have to, the very first task is to create an input tensor using the layer input and providing the shape of my input images. So that's my input image here that I'm having. Okay. Now I will create an autoencoder model. So this autoencoder model will contain two parts, my encoder and my decoder. Okay. So in this autoencoder model, I will pass my input tensor. That is the tensor that I created, my input tensor. Now the input tensor is a tensor of the shape 28, 28, 1. Okay. So here input image is my input tensor. So now what I'm saying is, over this input image tensor, the input tensor, apply con2D layer. So I'm saying over this input image, I will apply a convolution layer. So where the convolution layer will have 16 filters, each filter is size 3 cross 3, activation is ReLU and padding is same. So this is a convolution layer that I have defined. So I'm saying apply this image tensor and give me an output of it. So what this line of code, what the 15th line of code will do is it will take the input tensor, it will apply the convolution layer with these properties and give me the output con1. Okay. Then I'm saying that over this output con1, okay, you apply a max pooling tensor where my pool size is 2, 2. So over this con1, apply a max pooling tensor and then give me the next feature, my pool1. Then over this pool 1, apply another convolution layer that has 32 filters, 3, 3, and give me a feature map con2. And then over this con2, apply max pooling layer. So you can see here I'm using each of the layer as a function. That con2D is a function over which I'm passing a data, and it will return me a new data after applying the functionality of convolution. So similarly, max pooling is a function over which I'm passing some data, and it will return me some data after providing the max pooling operation. So finally, at the end of encoder, I will get, after the second max pooling, I will get pool 2. Now this pool 2 is my latent dimension, my latent feature vector that I have got is the pool 2 feature vector. So now comes decoder. So over the decoder, what I'm saying is, so this pool 2 was created by encoder. So over this pool 2, apply a convolution filter and give me con4. Now over this con4, I'm saying apply an upsampling layer. So rather than max pooling layer in encoder, here I want to increase the shape of my feature map. So over con4, I'm saying apply an upsampling layer to increase the size of the feature map. So upsampling will increase the size of this contour feature map and provide me up one. Then I am saying apply convolution layer over up one. Then again I'm saying apply upsampling layer over up two. And then I'm saying over up to apply a convolution layer to get me con 5. And over con 5 apply my final con layer. Now one thing we have to note is, see, whenever there's a con layer, the number of channels in the output is equal to the number of filters in the con layer. So let's say the number of filters in this con layer was 16. So the number of channels in con 5 will be 16. And number of filters in this con layer are 32. So number of channels in con 4 are 32. But the output image that we desire, it actually has to have just one channel. Okay. So that's why my final con 2D has only one filter, so that I can get my the one desired channel output. Okay, and since I know the range of the output, what say the last convolution layer has to actually provide me an image. Now I knew the range of my images are from 0 to 1. I know that. So that's why the activation over the last convolution layer will be a sigmoid activation. So that sigmoid activation, I can get the final decoded image in the range of 0 to 1. And finally, I will return my final feature map, that is my decoded image from this function of autoencoder.
How to make sure we'll get the same size 28 by 28 after
Okay.
the last layer? Yeah.
See, the thing that's making sure is, so will con2d decrease the size of the image? No.
Yes.
Will con2d increase the size of the image? No. Max pooling 2d will decrease the size of the image.
Yes.
So I am applying two max pooling 2ds.
Okay.
And then two corresponding upsampling 2ds.
Okay.
If I'm max pooling it 2 times, then I'm upsampling it 2 times.
Okay.
So that's how I'm making sure that the image size is the same.
And by the same size, 2 by 2. Okay.
Yeah, and you can see the pooling and upsampling has been done by the same size 2 by 2.
Okay.
So by this you can actually maintain that the shape of the final image is the same as the input. So this function is taking an input tensor input image and giving me the final tensor, the output tensor, the output image, that is my decoded tensor. Okay. Actually, I want to rewrite this line of code. It's actually a bit confusing. I don't want to write it in this way. So what I want to write this code at, so my output tensor is equal to auto encoder, and then I'm passing my input image tensor into auto encoder. Input image. So input image was the tensor that will have the input to the autoencoder, and I'm passing through the autoencoder function, and it will give me output tensor, the output to the autoencoder. Okay. So now I'm creating my encoder model. So now I have to create my encoder model. That is my model. Okay. So I'm creating a model in the name of model of the small m or small m. So now this model, so it's a functional API model. So first time I'm saying that to create a model. Okay. So I'm creating a model. So I'm calling the function model here with a capital M. So this function capital M will give me a model. Okay. Now in this model, I have to define two things. The first thing I have to define is what will be the input to the model. And the input to the model will always be the tensor created by the input layer. So the input to the model will be the tensor created by the input layer. So that is my input image. So this is the input to my model. And finally, I need to provide what will be the final output of my model. So in this case, the output tensor is the final output of my model. So here I'm using output tensor. So with this output tensor, I got the output of the model, and this input image was the input to the model. So now into this model function, what I've called is, you create a model starting from the input image tensor till the output tensor. So this model function will create a model. This whole model will create the model the way I've defined it and return me in this model with small m. So now this small m model is my final model that I've created. But rather than using the sequential API.add functions, I'm actually using the functional API, where each layer is treated as a function, and the final model has been created by the function model. And the task is to compile the model. So once the model has been created, we have to compile the model. So in compiling the model, we have specified the loss function, binary cross entropy, and we have specified the optimizer Adam. Now, since autoencoders are unsupervised, there's no class information that we are going to use. So there's no metric like accuracy or anything else, because here we are not doing any classification or anything. We're just reconstructing the image. So there's no metric in this case. So with these two codes, I have a proper model, an autoencoder model, which will take my input image and will give me the decoded, or you can say the output tensor. And this model has been compiled. Again, this line of code is useless. So finally, once my model is compiled, I can train the model using the function model.fit. Okay. So now, inside the fit function, the first argument that we pass is the input to the model, right? So input to the model will be the noisy image, because we are doing the task of denoising. So this is the input to the model, that is extra noisy. Okay. Then we will pass what the model has to create or generate, or the ground truth to the model. Okay. So in the ground truth of the model, what we want the model to generate the denoised image, to generate a non-noised image. Now extend had my non-noised image. So my Y label or my label to this model is my denoised image or the non-noised images. So I'm saying the model will get as an input noisy images, and it has to generate the denoised images. So similarly, I will give the validation data where I will say the model, the input to the model will be noisy validation images, and the model has to generate denoised validation images. And then I will specify the batch size and the number of epochs. And once this training has been done, I will save the weights of the model as encoder decoder model. Okay. So this will train the model for 2 epochs. The reason I've chosen 2 epochs was because the training takes a bit of time, like 2 to 3 minutes per each epoch. So the training happens fast. Okay. So now here I've created an autoencoder model which is being trained for denoising operation, which will take the noisy image and output me the denoised images. Okay. So I will go. So now let's say my model is trained. Okay. Let's say the model has been trained. Now my task is to use that model on testing data. So now my model is trained. Okay. Now my task is to use that model for testing data. So for that, what I will do is I will again define the model. Okay. I've defined the model again. And so I'm defining the model here. The prediction and convol. Okay, yeah. So I'm defining the model again here, the def autoencoder, which will take again my input image tensor as input. Okay, it will then apply my conv layers over the input, max pulling con, upsampling, and so on, and then I will get the final decoder, right? So, but while testing, I also want to see my latent dimensions as well. So that's the now this is something I want to show about my the model API. That is, I can actually create models which have multiple outputs. So now I want to create a model which does not just give me an output of my final image, but it also gives me the latent dimension that I want. That is the output of my encoder. So now you can see here the function autoencoder, it's returning not just the decoded image, but also returning the pool2. That is the output of my encoder. So here I'm creating a model which takes an input image, but returns me 2 things: decoded, the final output, the denoised output, as well as pool2 my latent dimension, the feature of latent dimension. So when I'm creating this model, what I'm saying is that the input to the model is input image, but the output to the model I'm getting from this function autoencoder. So now since this autoencoder is returning me 2 values, so the output of this model will be 2 different outputs of this model. So one is the final image and the second one is the latent dimension. So using this functional API, you can actually create the models that have multiple outputs. So why this is useful is, first of all, you want to see how the latent dimension is working, or you want to see how the activations are working. Secondly, in the case like inception, so we have seen in case if Sir has covered inception models, so inception we saw that the final prediction or the final loss function was not just taken in the final layer, but it was taken in the previous layers as well. Or even in case of variational autoencoders, where I need to have the loss function attached at two multiple times, at latent dimension as well and at final dimension as well. So there are many such cases in which I want a model that has multiple outputs. So for that cannot be created using sequential API. That can only be created using functional API. And for that, I just need to return two tensors from the model rather than just one tensor. So if I'm returning two tensors and saying that the output of my network will have these two tensors, it will automatically create a model with those two outputs. So finally, once this model has been created with two outputs, I can load the weights of the trained model, the model that I have trained previously, and then I can predict over the noisy data. Now see, this model had one input and two outputs. So if I use model.predict, I will give one input, my noisy data, and then it will give me two outputs. That is the final prediction, that is the DNOS data, and the con1, where con1 will contain my latent feature space. So for this particular image, it will give me the final DNOS image as well as my latent space as well. Because this model had two outputs, so I will get two outputs when I use the predict function, so from a single input. So this is how I can create a model which having the single noisy input and then two outputs, that is my final DNOS prediction, as well as the latent shape that I'm getting from the encoder. So encoder. Okay. So I can show you some of the results here because I've already trained and tested this system. So this was my DNOS images, that is X test. This was my noisy test images, that is X test noisy. And this is the system, the prediction that my autoencoder has generated. The reason you can see the predictions are really bad because the autoencoder has only been trained for 2 epochs. But if you train the autoencoder for 10 to 15 epochs, you can see it's actually able to denoise them very beautifully. It will actually create images that are pretty much similar to the above row. So if you just run this code for more number of epochs, you will see that you will get really good denoised images in this case. So this was about autoencoder. Any doubts? Okay, actually, can I take just a couple of minutes break? Yes, I don't have my water with me. I will just go and fill up my water bottle.
Yeah, sure, Daksh.
Okay, yeah. So sorry for that. I didn't have my water with me. So autoencoder is complete. Now we will be using all of these concepts to make a variational autoencoder. So the problem with autoencoder is it cannot create new data. So I can to an autoencoder I can actually give data noisy data, and then it will create a denoise version of that data, but it cannot create new data. But if I want to generate new data points, for that there is one generative model, that's my variational autoencoder. Okay, now since variational autoencoders actually take a lot of time to train, and here in this case I actually wanted to show you how the generation is done rather than just showing you some haphazard generations. I won't be using convolutional layers at all. I will be only making a model via dense layers, that is fully connected layers, so that the model is small, it can be trained easily, and you can actually appreciate that how it's able to create the new data points based on MNS data. Okay, so that's why you can see here. So when I'm importing the layers, I'm only importing the input layer and dense layer. So I'm not importing conv or max pooling or upsampling layers, because I won't be doing any of such operations in this case. So it will be completely fully connected based on network. Convolutional networks, these actually work better with convolutional networks, but to show you the generations as well, I'm using fully connected networks. So something about Keras is, till now we have seen that we are using inbuilt layers. So every time if we are using any layer, we're using an inbuilt layer, whether it be dense, input, conv, upsampling, max pooling. Okay, but what if I want to create my own layer? So there's a functionality that I want to encode that functionality in the form of a layer. So I have some custom function that I want to encode as the layer. So can that be done? Yes, that can very easily be done. So for doing that, Keras has provided me with a empty layer format, that's a lambda. So I can use this lambda layer to encapsulate any of the functionality that I want to make a layer out of it. So if I want to make any custom layer in my Keras model, I can make it by a lambda layer. But one point, this is very important point, that the lambda layer cannot have any trainable parameters. So this is very important point. So lambda layer can have any type of functionality over a tensor, but it cannot have any trainable parameters. So if there are trainable parameters in the lambda layer won't work. But if you have functionality that does not involve any trainable parameters, but you want to encapsulate that functionality as a layer of your model, you can use the lambda layer. So, so I will be showing how you can actually use a lambda layer for creating a new layer, a custom layer that will be having. Okay. So these are the three type of layers that we'll be using: lambda, input, and dense. Again, since VIE has multiple outputs and custom loss function, and again custom layers as well, so we cannot use sequential API. We can only use functional API. And we will be working on MNIST data. And here, since I will be creating a custom loss function, so for that, for creating a custom loss function, I cannot just use the compile and specify the loss function in the code. So for creating a custom loss function, I am importing the predefined loss function that I will be using to create a custom loss function. So I'm importing MSE and binary cross entropy so that I can actually create my custom loss functions using these MSE and binary cross entropy. Okay. And in the sixth line, I will come later on. What is the sixth import? I will explain this import a bit later on. I won't explain this import right now because it's actually a bit difficult to explain the sixth import right now. Okay. So so in this VAE code, what is the essence that we'll be seeing is how to create custom layers and how to create custom loss functions. So if you want to create a custom layer which is not defined by Keras, or you want to create a custom loss function, the loss function, the type of VAE loss function that is a bit complex. So how that can be done? So these are the two things that that is the actually part that we focus via VAE code. Okay. So the very first thing is that we have to import the data and pre-process it. Now, since the whole network is a fully connected network, okay, so the data that will go in the network will be of the shape, won't be of the shape of an image that is 28,28, but will be of the shape of a single vector of 784 dimension. Okay, so since in fully connected networks, any image that I want to input, it has to be first flattened. So I need to flatten my images of my MNIST dataset initially. So MNIST dataset has the images of shape 28,28. I need to create that shape as a 784, a single vector of shape 784. So for that, again, I'm using MNIST data in which my X-train is my training images of the size 28,28. And X test are my testing images of the shape 28,28.
This is same problem, denoising problem. It is a
No, this is generation.
okay.
We want to create new data of MNIST.
Okay.
So the so MNIST has 60,000 training images. So using those training images, we want to create some new MNIST data.
Okay. New data. Okay.
Yeah. So that's generation.
Okay.
It's completely different from what we have seen previously. So
Okay.
and none of the previous models were capable of generating new data. But this is capable of generating new data.
Okay. So any example of it?
An example.
Any practical example of some where we need this kind of learning?
Okay. Let me just show you some images. Okay, so this is one of the practical examples.
Okay.
Like actually, these are not that intuitive. So, for example, okay, like for example, one very good example of generation I can say it as you want to generate maps. Given satellite images, you want to automatically generate maps from satellite images like Google Maps. So you have all of the different type of maps. You have handwritten different type of maps, but now you want to create new maps. So that can. Another example is, see, any deep learning model actually requires a lot of training data. But whenever we work on real-time problems, in real-time problems, we don't have that much training data in hand. So many cases, what in real-time problems, we just have 100, 200 images. So cannot train a deep model with just on 100 and 200. So can we use these 100 and 200 images to create new images that belongs to that data set?
Okay.
So that we can train my deep model.
Okay. So coloring an image will not fall into it, this category. Like we have a black and
that
white.
would fall into generation, yes.
Okay. Okay. Okay.
Coloring an image will also fall into generation.
Okay. Variational, I mean to say variational autoencoder.
No, actually, see, in variational autoencoder, we won't be able to color. Okay, but in variational autoencoder, we will be able to generate new data.
Okay, generate. Okay.
So we will be able to generate digits that were not in the MNIST data set, but which correspond to ones. So we will be generating new ones. We will be generating new twos, new trees, and so on.
So we are going to increase our data set.
Yeah, we are going to increase the size of our data set. Okay. So even like search deep fake, DEEK. So this is something that's really good. Deep fake.
Okay.
Deep fake. Okay. So whatever images you are seeing here, they are all of fake images.
Okay.
Generated. So I mean, there are many good examples of generations. You can read about deepfake a bit.
Okay.
And what deepfake is, and actually the reason is deepfake is so bad that it has been banned for using it in. It's only used for research purposes. It has been banned for any other use. It was so good in basically what deepfake did was it was able to create. So let's say I have a video of President Putin. Okay, I can make him say anything I want.
Okay.
I can create a video of him saying anything that he has never said.
Okay.
I can generate a new video out of it, and it will be so wonderfully accurate that no one will be able to tell whether it's a fake video or a genuine video. So I can make anybody say anything.
Okay. Okay.
So
Okay.
this is one of the bad examples of generative models.
It would be interesting to see like how it will be like useful in the industry, our industries.
Yeah,
I'll go through it. Yes.
yeah. So basically, sir will cover the next topic that sir will cover is most probably GANs, generative adversarial networks.
Okay. Okay.
So in that GANs, sir will cover these type of things in details. That how to colorize an image and how to do such kind of stuff.
Okay.
Even even we will also see via code that how we can actually use such things to do learn a GAN.
Okay.
Okay, but today we're focusing on VAE, that is a generation model. It will help me in generating new images, and actually the main essence of using VAE is to learn two new concepts, that is making a custom layer in Keras and making a custom loss function in Keras. So according to me, that's the reason this VAE code is important. So one can learn these two concepts.
Okay. Thank you, Daksh.
Yeah. So here what we are going to do is, so as I've said, the X10 and X-test, they are images of the shape 28,28. But since we are using fully connected networks in this case, so we won't have to flatten these images. Okay. So now I need to specify the dimension onto which it has to be flattened. Now the images were 28 cross 28. So if I flatten this 28 cross 28, I need to get 784, that is 28 into 28. So here I'm specifying my original dimension, that is image size, that is 28 into image size, that is 28. So I'm saying that my so in original dimension I'm getting the value 784 to the shape size of the vector that I will be creating. Okay, so now X10 was 28,28. I need to convert this X10 into shape of 784, that is my original line. But precisely X10 just didn't have one image, it had 60,000 images. So X10 was 60,000 into 28 into 28. So it was a three-dimensional array. Now I need to convert this three-dimensional array to a two-dimensional array of size 60,000 into 784. So that is, I need to have those 60,000 images, but now each image, rather than being a two-dimensional array of 28,28, it will be a single-dimensional vector of 784. So for doing that, we will use a function np.reshape. So the function np.reshape will actually take np.reshape takes any array and then reshape that array into any size that we want. Okay, so I'm saying take the X10 array. Okay, and it has to reshape the X10 array to an array which has two dimensions, where the first dimension I'm specifying as -1. Okay, the size of the first dimension I'm specifying as -1. So whenever I specify any dimension as -1, that is, it has to preserve the original size. Now my original size of X10 was 60,000, 28, 28. Now in my final array, I want 60,784. So you can see, since the first dimension needs to be preserved, it does not need to be changed. So in the reshape, I've defined the first dimension is -1. So by default, it will know that -1 is equal to 60,000 here. So by specifying -1, it knows that it does not have to change this dimension at all. It needs to keep this dimension as it is. And finally, I am specifying here 784, my original dimension. That is, change the X10 array in the dimension of something, comma 784, where something it has to preserve from previous one. That is, change my X10 array in the shape of 60,000, comma 784. So this line of code will change my training arrays from the shape of 60,000, 28, 28 to 60,784. Similarly, we will do with the testing array, that is my X-test. I will preserve the first entity, that is 20,000 images. So in testing, I have 20,000 images. So I'm preserving the 20,000, but then I'm making it 784. So now my training data is now 60,784 and my testing data is 20,784. So now I have flattened each of the image with my training and testing data. Okay. Now I need to first convert this data into floating point. So I'm converting the data. So the X train was now 60,784, but it was still integers. So I'm converting into floating point and then dividing it by 255 so that I can get it into a range of 0 to 1. And similarly, I'm doing the same with my testing data. Okay. And now, so this is how I have pre-processed my data set. Now my data set is in the shape of 60,784, and each of the image is between 0 to 1 in floating point variable, floating point type. Now the model that I will be creating, now that model, the input shape to that model will be 784. That is my original dimension. It's a fully connected model. It will just get a 784 dimensional. So I'm specifying the input shape to the model here. That the input shape to the model will be a 784 dimensional shape to that model. So I'm specifying the input shape here. Okay. So now I will, okay. So VAE consists of two parts, my encoder and my decoder. Okay. Now my encoder takes an input and it gives me the mean and variance respective to that input. So that is my encoder takes an image, which takes the input images and provide me with the mean and variance of the distribution these input images belong to. So let me just recap it. So that is my encoder will take all of my input images and then for those input images, it will give me the mean and variance of the distribution on which each of these images belong to. Okay. Now encoder is a FC network. That is, it will take input at image. Image is of the size 784. Then it will have a hidden layer and then it will have a final layer. The final layer will give me mu and sigma of the distribution to which this input image belongs to, and I have an intermediate layer as well, the hidden layer as well. So when I'm making an encoder model, there are two hyperparameters. That is, what will be the size of my hidden layer and what will be the size of the mu and sigma that I need to create. So these are the two hyperparameters that I'm specifying here. So I'm saying that the hidden layer will be of the size 5, 1 to 12. That is, for encoder model or decoder model, the hidden layer will be of the size 5, 1, 2. So that I'm specifying as intermediate dimension. Okay. Then I'm saying at what batch size my network has to be trained. That's 128. Then I'm specifying my latent dimension. That is the dimensionality of the mu and sigma that my encoder will generate. So my encoder will actually generate mu and sigma of the dimensionality 2. And finally, I'm specifying the number of epochs this code will run. So there are two hyperparameters that I'm specifying: the intermediate dimension, that is hidden layer of encoder and decoder, and my latent dimension, that is the mu and sigma that I need to generate of the distribution of those images. They will be of which dimensions. Okay. Now, I'm skipping the sampling right now. We come to sampling later on, but first I want to cover encoder model. Okay, so the very first task of the VA is the encoder model. So encoder model, so you have to remember encoder model, okay, have two outputs. Encoder model has two outputs. Those two outputs are the mean and the sigma. So those are the two outputs of the encoder model. And then from that mean and sigma, I have to, so that the mean and sigma that is generated by the encoder, I have to sample a random data point from that mean and sigma. So my encoder, given an input image, will give me the mean and sigma of the distribution that image belongs to. But since I want to train the model for generation, I have to sample a point randomly from the distribution. So my encoder has finally three outputs. The first output is the mean of the distribution the image belongs to. The second output is the mean of the variance of the distribution the image belongs to, and third output is a point that is randomly taken from that distribution specified by mean and sigma. So my encoder model has three outputs from one particular image. Okay, so the input to an encoder model will be inputs, that is my input image. Okay, so first I will apply my first hidden layer, that is my hidden layer over this input image. So that's a fully connected layer which is of 5112 and activation is 0. Okay, so over this fully connected layer I will apply a dense layer. So over this X, that is my hidden representation that I have got, I will apply a dense layer of the latent dimension, that is my 2, to get the mean. So this dense layer will give the mean from this hidden dimension and will give the mean of the distribution this input image belongs to. And I will apply another dense layer which will give me the log variance of the log variance of the distribution this image belongs to. Now one peculiar thing here that we need to note is that the input image, so I had the input image as input. Okay, I applied a dense layer to get my hidden representation of X, that is a 512. So to get the mean, I have used this X, the previous X. So I've used this hidden dimension X to get the mean, and I have again used this hidden dimension X to get the variance as well. So you can see I have used two different layers on the same input to get two different outputs. So because I need to create mean and variance from the same image itself, so I need to have the same hidden representation of that image to give me mean and variance. So finally these two dense layer will learn to give me mean and log variance. So rather than variance we are using log variance. The reason is because variance can sometimes be really small, so we can actually and those small values can create problems in my network. So all of the computation that we will be doing in the loss computation will be on the basis of log variance. So we will be training the network to get my log variance rather than getting the variance, so that the small values can be scaled up using log. So this part is clear. So from the input image, I will get the mean of the distribution the image belongs to and log of variance of the distribution that image belongs to. So I've got my mean and log variance. Now my task is to sample a point randomly from the distribution specified by this mean and log variance. That is my sampling task. Okay. So that sampling task I've defined here. So this sampling task will get some arguments. Okay, so in these arguments, it will get two values, that is the mean and the variance. Okay, so this args will have two values, mean and the variance. So my first task is to extract the mean and the variance. So first of all, what I'm doing is from these args, I'm extracting my z mean and z log variance. So the mean and variance that I got here, I will pass to the sampling function, and then I will get my z mean and z log variance here. Now you can see this sampling function is something that the task of this function is, given this mean and variance, I need to sample a new data point. Okay, so that is the task of this function, that I need to sample a new data point based on this mean and variance. Right. So now this task, there's no layer for this task. Okay, so we have to create a lambda layer for this task. So we will come to that, how we have created a lambda layer for this task. But before creating a lambda layer, we will be making a function that actually can perform this task. Now another thing that needs to be noted here is that the z mean and z log variance, these are not NumPy arrays or any Python arrays. These are tensors. So these have, I've got these from applying some layers of the keras of deep learning. So these are tensors. So these are not my NumPy arrays or my Python list. These are tensors. So over a tensor, I cannot apply my NumPy functions. So over z mean, I cannot apply my NumPy functions. I cannot apply my list-based functions. So whenever I want to apply some property or some function over a tensor, like NumPy, I have similar to NumPy, I have a package called as a backend. So Keras has provided a package called as backend in itself. So this backend package actually creates some functionalities that I can apply over Tensor. So I can use this backend package to apply the functionalities that I want to apply over a Tensor. So like the functionalities here, like let's say I want to reshape a Tensor. So for reshaping a Tensor, I cannot use np.reshape. Okay, because it's not a NumPy array, it's a Tensor. And for example, I want to add two tensors, so I cannot use np.add. So I cannot use the NumPy functions. So, but yes, Keras has provided with a package for which has which I can use to apply functions over tensors. So here you can see from Keras, I'm importing the backend as K. So I'm importing the package backend as K. So any functionality of the package backend that I want to apply over Tensor, I can apply it via K. So now if I come back to the sampling function, I have Z mean and Z variance, log variance. Okay. So now I want to know what is the batch size. Because see, whenever I'm working with models, the tensor, the shape of the tensor will always be of the say batch size comma something. So batch size is always important. Despite we never specify that batch size as the shape while making the network, but while making custom layers, we have to always remember that the tensor is always in the format of batch size comma something, or batch size comma something, and so on. So the very first thing is I want to find the batches that I will be working on. Now since the tensor is of the shape batches comma something, so the batches is defined at the zeroth value in the shape of the tensor. So I'm taking the shape of the Z mean. Okay, so using the function k dot shape. Now here I cannot use the function np dot shape. I have to use the function k dot shape because Z mean is a tensor. So this k dot shape will provide me the shape of this tensor Z mean, and I will take the zeroth element of the shape, that is my batch size. So here I will get in the batch, I will get the batch size of my tensor that I'm working with. And now I need to get the shape of something. That what is the shape? What is the something shape here? That is, in this case, the something is my latent dimension. So for that, again, I'm using k dot shape, k dot in shape. In shape is basically similar to shape, but it turns the shape in integer format. Okay, and so I'm applying k dot in shape over Z mean, and I'm taking the first element of that shape. So by taking the first element of the shape, I will get the something that's my latent dimension, that is here 2. So here the Z mean one of the size batches comma 2. So over this shape batches comma 2, I will get batch as batch size and dimensionality as 2, that is my latent dimension. So basically this was very simple thing that I wanted to just extract the shape of the array Z mean, but again NumPy array, so I have to use k dot shape and k dot in shape. Okay. Now I've got the mean. So I've got the mean here and I've got the log variance. Okay. So I want to create a random point from this mean and log variance. So what is the way? Sir has actually discussed the way in which you can create any random point from given any mean and any variance. So what is the very first thing is you take a random point from a random normal distribution, a unit normal distribution. So the unit normal distribution will have mean at 0 and variance of 1. So if you take any point randomly from unit normal distribution, you can multiply that value with the variance and then add the mean to it. So let's say I have created a Z. This Z belongs to 0 1. Oh sorry, I have created Z. This Z belongs to 0 1. Okay, I want to create new Z which belongs to this mean and variance. So what I can do is I can say Z into variance plus mean. So now originally the Z belonged to the random distribution of unit normal. Now this new Z will now belong to a point from the distribution specified by this mean and this variance, the mean and variance. Okay. But what if I have log of variance? So in this case, you can see that I had log of variance, right? So what I will do is I will take exponential of log of variance. So in this case, since I was saying that we are actually computing log of variance, so for any point z which belongs to a normal distribution of 0 mean and 1 variance, if I want to create, if I want to project it into a distribution specified by a log variance and mean, so this is the function that I can use, that take the z from the normal distribution and then multiply it with the exponential of log variance and add the mean. But exponential function can and add the mean. Okay. Mean. So yeah, okay. Yeah. So using this function, what I will get is I will get a new point which will now belong to the distribution specified by the mean and the log variance. So you can see that the very first task will be to create a random point from my random normal distribution, that is 0, 1 distribution. So the task of generating epsilon or z in this, so I can write here e. So the task of creating an epsilon from a random normal distribution is I can use the function k dot random normal. Okay, so once I use this function k dot random normal, it will automatically by default give me a random point, give me random points belonging to a unit normal distribution. Okay, and I specify the shape of those random points. That is, by shape I mean that how many number of points I want to create and what will be the dimensionality of the each point. So by batch I've said how many number of points I want to create, and dimensionality is 2. That is what is the dimensionality. So here I'm getting let's say 32 images, 32 points, each of 2 dimension belonging to unit normal. So this epsilon now contains points belonging to the unit normal distribution. Now I'm scaling this epsilon, this unit normal distribution, into my distribution specified by my log variance and mean. So I'm using this epsilon, multiplying it by exponential of my log variance, and then adding the mean to it. Now finally, the point that I'm getting here will now be a random point that has been taken from the distribution specified by the mean and log of variance that I got from my encoder. So this is the sampling phase in which, given a mean and variance that I got from the encoder, I want to randomly take a point from that distribution. So to this function, now this is a function that will do this task. Now I want to create a layer of this function. So this is just a function that I've defined on tensors, but now I want to create a layer of this function. So to create a layer of any function, what I will use the lambda layer. So here I am using the lambda layer. So now lambda layer will create any custom layer. Okay. So in that lambda layer, I specify the function that it needs to encapsulate. So here I'm specifying the sampling function, the name of the function. Okay. So I'm specifying the sampling function that it needs to encapsulate. Okay. So what now this layer will do is, now it will create a custom layer which will do the same functionality as the functionality defined in the sampling function. Then I have to specify the output shape. Now the output shape. So what is the output that I'm getting here? I'm just getting a single point of the dimensionality 2, right? Of the latent dimensionality. So the output shape is latent dimensionality, and I'm giving the name of this layer as Z. So I'm naming this layer as Z, that it's my layer for getting the final Z. And so these are the properties of this lambda layer that I'm specifying. Okay, so now the line that I've highlighted, it's creating a lambda layer, okay, which will perform the function defined in the function sampling and will have this output shape. Now I want to give the input. So what will be the input tensors to this layer? Now, since this layer contains two input tensors, I'm providing these two input tensors as the list. So I'm providing the Z mean and Z log variance that I got from the encoder. So I'm saying that given Z mean and given Z log variance, this lambda layer will provide me a point Z that will belong to the distribution of Z mean and Z log variance. So if you want to create any custom layer, you can write any function that you want to apply over any number of tensors. Okay, you can apply any function, and this function can only have tensor operations, which will be used by the backend K, and finally use the lambda layer to encapsulate that function in the format of a KRS layer. So now this custom function, that was the sampling function, we've encapsulated as a lambda layer, and now this is a layer of my network, the sampling function. And now the encoder model. Now I have to finally create the encoder model, right? Now my encoder model will have one input, that is my input image. So while creating the model of encoder, I will specify the input, that is my input image, that's my input. Okay. And this encoder model has three outputs. That is my mean, the variance, and the final point that has been taken from that distribution. Okay. So my my encoder has three outputs: mean, variance, and the final point that has been made. So I've created an encoder model here. So now this encoder is a model that will take an input image and give me three outputs: the mean of the distribution the image belongs to, variance of the distribution the image belongs to, and the final point that has been randomly sampled from the distribution. So now this encoder model, I am returning the encoder model, and I'm also returning the tensors Z mean and Z log variance. The reason I'm returning these two tensors Z mean and Z log variance is I will be applying a loss function over these tensors. That is my KL divergence loss over these tensors. So that's why I need to return these tensors as well, because that is a loss function that I want to apply. So this function will take an input tensor as an input image and return me an encoder model and return me two tensors, the mean and variance tensors. Okay. So here you can see that I've created this, so I can just run it. So here you can see I've created this input, and this is the summary of the input. So this model will take input a 784 dimensional image. Okay, so it will apply dense one. So it will apply dense one and give me hidden dimension. So over this dense one, it will apply another dense to give me the Z mean. And over this same dense one, you can see over this same dense one, it will apply another dense layer to give me log variance. And over the mean and log variance, it will apply my lambda layer to finally give me the point Z. So you can see that the model, how the model is, the summary of the model. And so this is my encoder model, that given an input image, I'm getting three values, that is the mean, the variance, and 1 point extracted from that mean and variance. So finally will be my decoder model. Okay, so decoder model will actually, the input to the decoder model will be input tensor of the latent shape. That is this Z, the Z that I have got from my encoder model. So first of all, I'm specifying an input to my decoder model via using input layer, and the shape of the input will be latent dimension, that it will be a two-dimensional vector. So the first part for the decoder model is specifying that input layer. Okay, so now over this latent input, I've specified as my input layer. Over this latent input, I will apply a dense layer and get my hidden representation. And over this hidden representation, I will apply my final dense layer to get my original dimension. That is a 784 dimensional vector with activation sigmoid, so that I can get my final output. Okay, so this final output will be now my image of the size 784 with activation sigmoid from the input, the latent input Z. That I go latent input Z as input and give me the outputs. That is my final image, the tensor named outputs. So this is my decoder model, and then here I am just returning the decoder model. Okay, So decoder model is a pretty simple model. You can see here that the input is a two-dimensional data point extracted from encoder, and the output of this model is the final image that I want to generate. Okay. Now here I'm finally just creating the final VAE model. So VAE model will have the inputs. So this was the inputs that I generated for my encoder. So to the encoder model, I gave this input. So this input is my input image. So my final VAE model will take the input image, okay, and then it will provide me with the final output. So my final VAE model will take the input image and will give me the final output. So that's my VAE model. And that is my final VAE model, which I've created here using the model API. That is, take the input image and give me the output image. And this is the summary of the VAE model. A simple summary: it will take the input image, it will pass it to encoder, and then that the output of the encoder will be passed through my decoder, and I will get the final image as output from the decoder. So this is my VAE model containing encoder and decoder, where encoder takes an image and gives me three outputs, and decoder takes the one output from the encoder, that is the data point, and provides me with the final image that I'm having. Now comes the second task, that I want to create a loss function. Okay, so now the loss function of VAE contains two parts. The first part is a mean square error loss function, which will be applied over the output of the network. Okay, so now the very first task of this VAE network is that this output of this network should be similar to the input of this network. So that's a very first task, right? So that is the output that the network has to generate while training has to be similar to the input that was given while training. So that is the first reconstruction loss that we are specifying. That is, the output that you generate and the input that was given to the network, the mean square error between them. That is, we have to minimize the mean square error between the input and the final generated output. So that is a reconstruction loss.
Daksha, I have one question. Encoder is giving two output, input layer and model. Which one we need to consider?
Okay. Okay, encoder is actually giving three outputs: the mean, the variance, and the final data point.
Right.
Right. So for making the VAE model, we will consider the final data point.
Means lambda, right?
Yeah, the Z.
Okay.
Okay. So let me just show you what has happened. Okay. See. So when I made encoder model, I said this model will have three outputs. The first output will be the mean. The second output will be the log variance, and the third output will be my Z, my final data point. Okay. So this is my 0th index, this is my first index, this is my second index. So when I'm creating the VAE model, so you can see here. So when I'm creating the VAE model, okay, I pass my input image to the encoder. I pass my input image to the encoder. Now this will give me three outputs: the 0th, the first, the second. And since I have to now to decoder, what I have to pass? I have to just pass the second index output, that is my Z. So I will take the second index output from that is my second index output, and I will pass it through my decoder. So I can actually rewrite these lines as, okay, so test is equal to I pass this input to the encoder. Now I will get three values. So now I will take test2 is equal to test2. So now these three values from the encoder contain mean, variance, and data point that I extracted Z. So now I'm saying from these three values, you take the data point Z. So Z was at the second index. So I will get the test2 test2 as the data value Z. And finally, I will do output is equal to decoder That's true. So I will pass that value Z from the decoder to get my final image outputs. So I can comment this line. So now you can see that from the input will go to encoder. It will give me 3 values. Okay. So from the 3 values, I have chosen the last value, that is my value at the second index, and that value I have given as input to the decoder to get my final output. So my final model will give the input image and will return me the final output.
Right.
So yeah. So all of these 3 lines were actually written in just one single line in this line. So this line does the same part as all of the 3 lines, the above 3 lines. So it takes the input, pass it to encoder, takes the second index out of it and pass it to decoder. So all of the above 3 lines were just written in one line to get my final output. And
Yeah.
finally, I've got my final VAE model.
Got it. Got it. Thanks. Thanks.
Yeah. Okay. So for creating the loss function of my VAE model, I have 2 loss functions. One is the reconstruction loss, and the second one is scale divergence loss. Actually, see, I won't be going in details of how the loss function that I've defined here is scale divergence loss, just because it's a bit of math behind that, which sir has covered in the theory. Okay, so I won't be going into the math of that because sir has already covered in the theory. But uh, so what I'm doing is I'm first just making my reconstruction loss. Okay, so my reconstruction loss is just the mean square error loss between the input and output. That is, the input will be the input image, and the output the VAE has to generate, it has to be same as the input image. So that's my reconstruction loss. Now my second loss is that the Z mean and Z log variance that I got from encoder, they should be closer to my unit normal distribution. So Z mean should be closer to 0 and Z log variance should be actually closer to 1. That is the distribution that is defined by Z mean and Z log variance. That distribution should be closer to unit normal. That is, KL divergence between the distribution specified by Z mean and Z log variance should be closer to the KL divergence of the distribution specified by 0 mean and 1 variance. Okay, so I'm not going to go into details, but these 3 lines are doing that very thing. So these 3 lines are computing the KL divergence between my Z mean and Z long variance and my 0 mean and 1 unit variance. I know it's a bit counterintuitive, but I can't go into maths right now. Okay, but these 3 lines are providing me with the KL divergence between Z mean and Z variance and 0 mean and 0 variance distributions. So finally, I have the reconstruction loss and I have the KL divergence losses, KL underscore loss. So I'm going to add the both losses, reconstruction loss and KL loss. And then I'm going to take mean of these 2 losses, K dot mean. So this is my final VAE loss. So this loss contains 2 losses, reconstruction loss and KL divergence loss. And finally, I have taken mean of those 2 losses to get my final VAE loss. So just you can, so this is my custom loss function to create my VAE loss, which computes my VAE loss. Okay. Now I want to add this loss to this VAE model. So I want to compile this model using this VAE loss. So what I will do is I will use the function add loss. So every model created in Keras has a function add loss in it. So I'm taking the model VAE, the VAE model that I created. I'm saying to this model, add the loss defined by VAE loss. So this VAE loss, which has been defined by a combination of reconstruction loss plus scale loss, it will add this loss computation to this model. Now this model will compute this loss function, a custom loss function. So if you want to compute a custom loss function, you can write that custom loss function, whatever loss function you want to compute it, and then just use the add loss function of a model to add that custom loss function. And the model has been created. We have added a custom loss function. Finally, we will compile our VAE model. Now here, while compiling, since I've already added a loss function, I don't have to specify the loss function. I just have to specify my optimizer. Sorry for that. So I just have to specify my optimizer. So because here I've already added a loss function in the previous line of code, I don't have to specify a loss function here. So in these two lines, I've compiled the model with the loss function defined by VAE loss and my optimizer added. So here I've used the custom loss function for VAE and I've compiled it with Atom Optimizer. And so once all of this is done, now my model has been created. My model has been compiled. I can just train my model. Now you can see this model, while defining any loss function, I didn't define the loss function over some label. I didn't specify any label. I have defined the loss function over the inputs and outputs defined by the model itself. There was no label involved, or there was nothing from the outside involved. So the loss function had been defined by the tensors inside the model itself. Input was the input image, output was the generated output, and mean and variance were also the internal tensors of my model. So since there's no label involved in this, and all the loss function has been defined is via my internal system only. So while training, I have to just specify my input X string. I don't have to specify any labels because this loss function does not have any labels at all. The loss function is completely applied over the internal tensors. So while training as well, I just have to specify the input to the network. So I have to just specify the inputs to the network. That is my X train. So it will automatically apply all the loss functions over this input X train without the use of any labels. So in the fit here, I'm just giving X train. I'm giving no labels at all. Then I'm specifying the epochs, then batch size, and similarly for validation data. Again, for validation, this network does not need any labels at all. So for validation data, I'm just giving X test and I'm giving no label, none. I'm not giving any label at all. So for training the VAE in the fit, since this loss function has been made in such a way that it does not require any labels, it's just on internal tensors. While fitting also, we don't have to give any labels at all. So we can train the VA using this fit command, and finally after training we can save the weights of the VAE. So this is already a training that has been done. Okay. So after training, what I did was so for the testing data, okay, I wanted to see what kind of distributions my network has learned. I wanted to see what kind of distribution my network has learned. So for visualizing this distribution, okay, so what I did was I took my testing images and I passed them through the encoder. So I took my testing images and I passed them through the encoder. Encoder will give me three values: mean, variance, and random point sample. So I'm not taking my variance and random point sample, I'm just taking my mean, and then I'm plotting the mean for different classes. So you can easily see here, each class is being plotted by a different color. So color. Now, see, in VAE, we never provided any class information, but VAE learned on its own that all of the zeros are similar to each other, all of the ones are similar to each other, and so on, and all of the nines are similar to each other, and so on. It automatically learned on its own the distribution of my whole data. So this is the distribution that I have shown of the data that the VAE has learned. That is how the means are spread. So this is the distribution of the data that my VAE has learned after training. And finally, these are just some reconstructions. So finally, what I can do is now my task is I want to generate new images. So for generating the new images is being done by here. Okay. So here I'm generating new images. and also plotting them. I'm not because this code is a majority for plotting. So what I'm doing is I'm creating a numpy array. I'm creating a random numpy array, which random numpy array, and I'm passing this random numpy array through the decoder. That is, I'm creating random samples of Z, which are not taken from encoder at all, but just I'm taking some random samples of Z and I'm passing them to decoder to get my some images. Okay, so here you can see these are the images that have been generated by these random numpy arrays. So these Zs, these latent vectors were not computed by my data set, but I just took some randomly, I created some Z values and then I passed them to the decoder. So you can see here that these are all the images that the network has generated now. So these are all the images that have been made by the network by passing any random Z to the decoder. So you can see here, so over this region it's able to create some zeros. Over here it's able to create some ones. Here it's able to create some sevens. Here you can see some fives and some threes and eights and so on. Somewhere here you can see nines as well. So you can see here nines. So you can see the network is now able to generate new MNIST images from random samples, from random noise samples. Go to the decoder. So I'm just take any random sample and throw to the trained decoder and it will generate a new image that belongs to the distribution of MNIST dataset. So this is so these are the images that I have created, the new images that I've created of MNIST datasets. So since these images are really small, all of these images have been clubbed to show in one image itself. So, but these are all so each of this is a single image that this is a single image that MNIST created. This is a single image that MNIST created. This is a single image and so on. So each of these digits is a single 28 by 28 image that the VAE created, and these are the different type of images that it was able to create. So these images were not present in the data, but it learned to create these images by learning the distribution of my original data using the network that we have defined above. So I hope this thing is clear to everyone. So this was it about VAE as well. Any doubts over the VAE? So am I audible or there's some issue?
Yes, Daksh, you are audible.
Okay, so Yeah, so that's it for VAE. Any doubts?
I'll go through once again, Daksha. Go in between. I took some breaks, so I'll go through once again. If any doubt, then I'll let you know.
Yeah, sure. You can let me know.
Yeah.
Okay. Yeah, so that's it for today. So next time I will try to create a. I will ask sir about it. I will discuss with sir about it and how we can use a real-time scenario for our.
Yeah, that would be good. Yes. Thank you, Daksh.
Yeah. Okay. You're welcome.
Yeah.